Good morning, students. Today we will study the new technique mass spectrometry. Actually, it is not new to you people because in previous semester we had studied introductory part of this technique. The basic functioning of the mass spectrometry is that the sample is vaporized and it is bombarded with high energy electron beam which will cause the ionization of the sample, and the ions are accelerated under the effect of electric field. The accelerated ions are separated according to mass to charge ratio under the influence of magnetic field, and these separated ions are detected by detector according to their abundances or depending on the number of ions produced of that particular type. Now let us see the functioning of mass spectrometer. Mass spectrometer has different components. One is sample reservoir. This is our sample reservoir. Then we have a ionization chamber. We have a analyzer chamber. We have a recorder. Now let us see the sample. The sample required for mass spectrometric technique is usually gaseous sample, but we can have gas, solid or liquid also. All the types of the samples, that is solids and liquids, are also converted into gaseous form. A sample reservoir is there, or this is the sample container through which a gaseous sample can be introduced into the ionization chamber. This small entrance is there through which the sample is entering into the ionization chamber. That entrance is called as molecular leak. Molecular leak is name given to that because it is a small hole and molecules are leaked into the ionization chamber through this small entrance. That's why it is called as molecular leak. Through the molecular leak, the sample can enter into the ionization chamber. Usually the inlet system, that is our sample reservoir and this small entrance, these are partially evacuated so that the ionization chamber is at low pressure than the sample inlet system. For gaseous sample, there is no problem. Sample can be easily introduced into the ionization chamber. Even the volatile liquids and uh, solids, they are also introduced into the ionization chamber. But for non-volatile or less volatile materials, the system is designed to fit into the oven, which can heat the sample to provide the greater vapor pressure. Non-volatile samples also can be introduced by using a probe. A small syringe-like probe is there, and at that tip of the probe, a sample can be placed, and that probe can be heated to convert the sample into gas. But now, if the probe is used, then directly the sample is introduced into the ionization chamber. That probe, as it is heated, it will convert the sample into gas. The sample is introduced into the ionization chamber, where the ionization chamber is having different components. One is repeller plate, it has accelerating plates, and it has a preheated filament which will create a high energy electron beam. Electrons are generated or ejected by this filament, and the electrons have very high energy, and that high energy electrons are used to bombard the sample. When sample is bombarded with these high energy electrons, the molecules get converted into ionization ions. That is, ionization process is occurring in this region. That's why the chamber is called as ionization chamber. The ionized sample, then it is accelerated towards forward direction through these negatively charged accelerating plates. A high potential difference is applied across these plates, and as they are having negative potential, the ions are accelerated through these accelerating plates. One plate is their repeller plate, which is positively charged plate. Now, once the sample is bombarded with these high energy electrons, the sample molecules can be converted, or they get converted into positively charged ions. Some of the molecules are converted into negatively charged ions, and some remain as it is. That is, the neutral molecules are still there. So this part will have positively charged ions, negatively charged ions, and some neutral molecules. The positively charged ions are repelled by this positively charged repeller plate. It will repel. Positive charge repulsion will be there, and they will repel. And this plate will force the positively charged ions to move in a forward direction. This positively charged repeller plate will also absorb the negatively charged ions generated here and the extra electrons here. Then the positively charged ions are attracted by these accelerating plates as they have negative potential, and they will be focused through these slits. Small hole is there, that is called as slit. Through these slits, the positively charged ions are accelerated into the new chamber that is called as analyzer chamber. Now, in this region, the ions generated are usually positively charged ions generated. Let us consider that a molecule as M, and when it is bombarded with high energy electron beam, the electron, this high energy electron will remove one more electron from this molecule, and the molecule will get converted into ion, positively charged ion. So this ion is called as molecular ion because from the molecule we have removed one electron. Now, depending on its stability, either it will be accelerated directly towards the analyzer chamber, or it may undergo fragmentation in the ionization chamber itself. If it is unstable, M plus, if it is unstable, molecular ion, if it is unstable, it will be disintegrated, or it will be fragmented into the ionization chamber into smaller fragments, and depending on their stability, their abundance will be there. Now, once the sample ions leave the ionization chamber, they enter into a small field free region. From this field-free region, the neutral molecules and some of the negatively charged ions are removed from the mass spectrometer through this vacuum pump. So through this part, the negatively charged ions and neutral fragments are removed from the mass spectrometer or the ionization chamber. Only positively charged ions are forwarded, or they are accelerated in the ionization chamber. After this field-free region, there is a region where magnetic field is applied. Under the influence of magnetic field, these positively charged ions travel in a circular fashion. So look at this, this circular fashion is there. But the mass spectrometer is designed in such a way that it will have only half circle. Otherwise, if you see, you can see that the ions can be in a circular, or they travel in a circular pathway. These circularly traveling ions are then separated into different beams according to their mass to charge ratio. So look at this, the positively charged ions are separated according to their mass to charge ratio. Different beams are generated, and then these are collected by a collector, and it is given to the recorder. Recorder will record the mass spectrum, which is actually the record of the number of positively charged ions generated and their mass to charge ratio. So according to their M by E, the spectrum is recorded. Very important thing is that only positively charged ions are detected. Neutral species are not detected by mass spectrometer. So this is how the mass spectrometer works. Now these accelerated ions in the ionization chamber, they have certain kinetic energy, and that kinetic energy is expressed in this form, or this is the formula which will express the kinetic energy of those ions. Half mv square is equal to E into V, where m is the mass of the ion, E is the charge on that ion. Then we have one more equation that will give me the radius of that curvature. Then we have this V, capital V is there, which is the potential difference applied across the accelerating plates. Okay. Now, in presence of magnetic fields, just now I told you that the ions follow a circular pathway. The radius of that circular pathway can be given by this formula mv upon eh, and then by substituting these values here using this equation and this radius equation, finally we get a new equation which gives me m by e is equal to h square into r square upon 2 into v, where h is the strength of applied magnetic field, r is the radius of that curvature, and this v is the applied potential difference. When these ions are separated, the large mass containing ions are will be having larger radius of the curvature. For example, this is the tube, or we can go back. See, this part will have large radius. If you consider this as a circle, this region will have large radius and this will have small radius. So the ions with larger mass will have larger radius of the curvature, and smaller mass ions will have smaller radius of the curvature. Now let us see some parts of the mass spectrum. Mass spectrum has different components, or it can be described or it can be viewed through different aspects. It is a plot of ion abundance versus mass to charge ratio. Then what we should look into the mass spectrum? We There are different components of the mass spectrum. One is base peak. This is the most intense peak in the mass spectrum. It can be sometimes the base peak can be a molecular ion peak, or it can be a fragment ion peak. Then we'll consider the second part in the mass spectrum is molecular ion, or second term related to the mass spectrum is molecular ion. Molecular ion is the heaviest peak in the mass spectrum, or this is having highest mass to charge ratio peak. M by E is the mass to charge ratio. Then one more term is there, that is fragment ions, and one is there isotopic peaks. Isotopic peaks are also recorded. Usually the elements, they can, or the different elements can exist in isotopic forms, and those isotopes are also detected in the mass spectrum. Let us see this example of a mass spectrum. This is one compound, butane is there. This is the mass spectrum. Look at this relative abundance. Relative abundance means how many ions of that particular fragment are present, or how many ions are present. And the x-axis is having mass to charge ratio. Look at this, the peak at 58 is the highest or heaviest peak in the spectrum. So this is called as molecular ion peak. Molecular weight of the butane is 58. We are having a peak at 58. So this peak is called as molecular ion peak. We can find out the molecular weight of the compound from this peak. Now we have smaller parts or smaller peaks here. Intensity of these peaks are different. Molecular ion peak intensity is less. Now we have one more peak, which is the most intense peak in the mass spectrum. The most intense peak in the mass spectrum is called as base peak. Base peak is considered as having 100% intensity, and with respect to this peak, the other peak intensities are described. Let us say this peak at m by e 43 is having 100% intensity. The other peaks are described in that. According to that, let us consider that this m by e 29 is approximately having 45% intensity. It's per 45% intensity. Other, you can see this peak at 15 is having very small percentage, is less than 10, so its abundance is less. So this is the most abundant fragment, or this peak corresponds to most abundant fragment. So the as the fragments generated here are most of the times positively charged. Most of the times these are carbocation type of the fragments, and depending on the stability of that carbocation, the peak intensity is there. So if I see this, M by E 58 intensity is very small and M by E 43 peak intensity is very large. This means that this peak is due to a stable carbocation, and M by E 58, that is molecular ion, is having less stability. So this concept of base peak, intensity, molecular ion is covered in this part. Now fragmentation. Ions which have lifetime less than 10 raised to minus 6 second, they undergo fragmentation in the ionization chamber. This is very important fact. And then they are converted into smaller fragments. Some neutral molecules are also removed from this ionization chamber. Now ions with lifetime of the order of 10 raised to 6, 10 raised to minus 6 second, they are accelerated to the analyzer chamber, and they can disintegrate in the analyzer chamber. Fragment ions thus produced follow an abnormal path. These ions appear at m by e that depends on its mass as well as the mass of original ion from which it is formed. Such type of the peaks are called as metastable peak. For example, this is M1 molecular ion. Let us consider that this is first fragment, and it is disintegrated into another fragment which is having lifetime of the order of, or approximately its lifetime is equal to 10 raised to minus 6 second. Then what happens? Then a new ion or peak is recorded at the m by e value, that is called as m star is equal to m2 square upon m1. Such peaks are called as metastable peaks. Now this is another concept or another thing which we should know. The natural abundance of different elements will affect the appearance of the mass spectrum. Some of the elements can exist in isotopes which are heavier isotopes which have considerable abundance, and some of the heavier isotopes have very less abundance. The commonly found elements in organic compounds are hydrogen, carbon, sulfur, chlorine, bromine. These are the most important elements. Now their isotopes are different. Isotopes are there. The hydrogen is the most common isotope is H1, but its heavier isotope is H2, that is deuterium is there. Its natural abundance, if you compare, 99% of the hydrogen is H1, 99.98% is hydrogen H1, while deuterium H2 is only 0.01%. Carbon exists in a C12 as well as C13 forms. C12 is having 98.98% natural abundance. That is, this is most abundant isotope of the carbon, and the less abundant isotope of carbon, carbon 13, is having only 1.1% natural abundance. Sulfur is existing in two different forms. One is sulfur 32 and one is sulfur 34. Sulfur 32 is having natural abundance 95%, while the sulfur 34 is having approximately 4.2%. Similarly, halogens, especially chlorine and bromines, they are also existing in two different isotopic forms. Chlorine exists in chlorine 35 and chlorine 37. Chlorine 35 is having 75.5% existence, while its heavier isotope is having 24.46. Approximately 3:1 ratio is there for this isotopic existence. Another very interesting thing is that bromine exists in bromine 79 and bromine 81 isotopic forms, and approximately their existence is 50%. Look at this, bromine 79 is having 50.52%, while bromine 81 is having 49.48%. Approximately they are existing in equal amounts. So these differences in their natural abundances affects the mass spectrometer to a great extent. Largely the mass spectrometer is affected by these different isotopes. Due to the presence of these isotopic elements in the mass spectrometer, isotopic peaks are generated, and these isotopic peaks are recorded in the mass spectrometer. This is the formula which will tell us the intensity of isotopic peaks. Usually A plus B raised to n is the formula which will give me the intensities of peaks or isotopic peaks, where in this formula A is the relative abundance of lighter isotope, that is smaller isotope. B is the relative abundance of heavier isotope, and n is the number of atoms present in that molecule. For example, a molecule is having only one chlorine atom. Let us consider one chlorine atom. Then what we have, the isotopic peak will be there, and let us consider that molecular ion is, this is the M. Will have one more peak at M plus 2. The intensity ratio of these two peak will be 3:1 ratio. That is, molecular ion peak will have the intensity 3, M plus 2 will have 1. So as the abundance ratio is 3:1, if the molecule possesses two chlorine atoms, then what happens? A plus B square is there. A plus B square is then the equation, if it is expanded, then it will be converted into A square plus 2AB plus B square. This is the expanded form of the this equation. Now A is the lighter isotope. Lighter isotope is chlorine 35. Chlorine 35 is having the relative abundance 3. So it will be 3 square plus 2 into relative abundance of chlorine 35 is 3. Relative abundance of chlorine 37 is 1. So it is 2 into 3 into 1, and plus B square means it is 1 square. So this is how you will get that 9:6:1. So what is this 9:6:1? Now in this case, when there are two chlorine atoms, we will have three isotopic peaks. The three isotopic peaks are separated as M, then we have M plus 2, and then next peak will be M plus 4. The intensity of these signals, M plus 4, intensities will be in the proportion of 9:6:1. So M will be having intensity ratio of 9, M plus 2 will be having intensity ratio of 6, and M plus 4 will have intensity ratio of 1. So intensity ratio for these isotopic peaks will be 9:6:1 for chlorine. These are some patterns for isotopic peaks. Look at this, depending on different elements, we can get different number of isotopic peaks. For one chlorine, we have M and M plus 2. For two chlorines, we have M, M plus 2, M plus 4. If we have three chlorine atoms in the molecule, then the mass spectrum will record M, M plus 2, M plus 4, and M plus 6. If one bromine is there, we have M molecular ion and M plus 2. The intensity ratio, if you check, the intensity ratio are very interesting. For one bromine, we have equal intensity peaks of M and M plus 2. So this is how the peak intensity or the molecular ion peaks can be observed in the mass spectrum, and they will be used to find out the presence of that particular element. How these isotopic peaks are used in structure determination, that we'll see in the next lecture, and we will have some facts related to the mass fragmentation in the next lecture. So